Microscopic form means the expression of resistance in terms of current number density of electron, charge, relaxation time, everything. Yes. So the expression of resistance that we know is V by R. Now I need the expression of same resistance in terms of microscopic variables. Microscopic variables means number density, relaxation time, mass of electrons. The variables in terms of which we defined drift velocity, in the terms of same variables, I need the expression of resistance. So for that, we can start with the calculations with this conductor. This is the conductor, area of cross section is A, length of the conductor is L. We connect it to a battery of voltage. Amalia, what is the expression of current flowing through this conductor in terms of drift velocity? Yes, Amalia, do you remember any formula for current passing through this conductor in terms of drift velocity? Yes.
NEA.
Sorry? Expression of current in terms of drift velocity, bache. Okay. Amalia did not remember. Sania. What's the expression of current in terms of drift velocity?
Sir,
T by L VD.
NEAVD. The second calculation that we did,
Yes, sir.
I is NEAV. Now, to get this expression in terms of resistance, first of all, let's substitute the value of drift velocity. Shahzada, what is the expression for drift velocity? We derived it yesterday.
also
Yes, Shahzada, drift velocity.
the L will
Oh, see how by. Well, let's substitute this 2 in 1. When I substitute 2 in 1, I will get I is NEA VD, which is EE tau by M. So your I is N E square A E tau by M. So this is your current. N E A square tau by M. This is a current in terms of electric field. E is electric field. Huh? E is electric field. Electric field. Abdullah, do you remember any relation between electric field and voltage? Electric field and potential difference, Abdullah? Do you think of any relation between electric field and potential difference? No. Mariam, can you think any relation? Can you remember any relation between electric field and potential? Ahmad? V is voltage, potential difference. Noor?
So E is equal to minus V by R.
Gradient of potential. Huh? We have used this relation in capacitance several times. Huh? E is V by R. That is the equation. Electric field is the ratio of potential difference and length. Gradient of potential, electric field is gradient of potential. Now I can substitute this 4 in 3. When I substitute 4 in 3, I will get I is NE square A tau over M Electric field is potential difference divided by length. From this equation, I can get the ratio of V by I. So I can write that V by I is ml over a n e square. And V by I is nothing but resistance. You can say that resistance is ml over a n e square. So this is the expression of resistance in microscopic form. This m is mass of electron. This is electronic mass. Electronic mass. Noor, microscopic form means expression of resistance in terms of microscopic variables like number density, electronic mass, relaxation time. These all are microscopic variables.
Okay, sir.
From this, by the way, what is n? Ahmed, what is small n here?
Number of electrons.
Just number of electrons, small n. Just turn your pages. I have defined this small n. Just turn pages, come to second derivation of relation between current and drift velocity. See, what is small n there?
It's a free electrons. Number density of free.
Number density. What do you mean by number density? It's number of electrons per unit volume. Small n
Yes, sir.
are not total number of electrons. That's number density. Number density means number of electrons per unit volume. What is tau here? Sania. What is this tau? This symbol tau means here. Sania, what this symbol tau means here?
It's the direction.
Direction. Mariam, what this tau represent here? Tau shows relaxation time. We used relaxation time yesterday. This is the formula for drift velocity. In drift velocity, we use this relaxation time. What was relaxation time? Time taken between two successive collisions of electrons and ions was relaxation time. Anyway, this is the formula of resistance. R is ml by A n e squared. ml by A n e squared. So you can say that resistance is directly proportional to length. It's inversely proportional to area of cross section. And it also depends upon number density as well as relaxation time. So we can write that resistance of a material depends on first length. So R is directly proportional to length. Area of cross section. R is inversely proportional to area of cross section. Resistance also depends upon number density. This number density will depend upon the nature of material. Different materials will have different number densities. Like if I take iron, iron will have lesser number of electrons than copper. If I compare copper and iron, then copper will have more number of free electrons than iron. So this small n will depend upon the nature of material. Okay, can you compare gold and copper? Which one is a better conductor, Shahzada?
So the copper.
Oh, copper. Okay.
The gold.
Gold is a better conductor. So Shahzada, what do you think? Which one should have more number of free electrons, gold or copper?
So gold.
Gold is a better conductor, so it have more number of free electrons than copper. So it also depends upon nature of material. It also depends on nature of material. Fourth. After nature of material, the next is relaxation time. The resistance also depends upon relaxation time. When I say relaxation time means temperature. Relaxation time is a function of temperature. It depends on temperature. So these are the four factors on which the resistance of a material depends: length, area, nature of material, and relaxation time. See, I'm not considering M and E here because M is the mass of electron, which is a constant term. It does not vary from one material to another material. You cannot change the mass of electron. E is the electronic charge. This also does not vary from one material to another. I'm considering also this as a constant. All other are variable. We can find number of electrons in metal by atomic number. No, we just don't need just atomic number because atomic number tells you about the total number of electrons. Not all electrons of a metal are free. Along with atomic number, you should have an idea about the number of free electrons. This extra detail must be given in the question. Like copper have 2 free electrons. Although this atomic number is some 20, 28, 29, I guess. But the number of free electrons that copper have is only 2. Per copper atom, donate 2 electrons. The number of free electrons is not equal to atomic number. So that was about resistance. Okay, just note it down. Then we'll start resistivity. Yes, can I change this right now?
Yes, sir.
No, sir.
Okay. Tell me once you have written. Yes, Amber, can I change this right now?
No, sir.
No. Oh.
So what is this? An electron.
Mass. The mass of electron.
Okay, sir. So done.
Okay. After this, the next thing is resistivity. So resistance depends on length as well as area of cross section, right? If I define a quantity like resistance, but that quantity is independent of length and area of cross section. Like if I remove the dependency of length and area of cross section from resistance, the quantity that I'm left with is resistivity. Like if I remove this L and this A, obviously it's not resistance. This is another quantity which is known as resistivity. Resistivity also defines obstruction offered by a material in the flow of current, but resistivity is independent of length and area of cross section. So this is how we define resistivity. Resistance is directly proportional to length. It's inversely proportional to area of cross section. When I combine these two things, I can write this as this is proportional to L by A. When I remove the sign of proportionality, I will use a constant which is rho. It's rho L by A. This rho is known as resistivity. This rho is resistivity. So I can write resistivity as R A by L. I just cross multiplied here. This is the formula of resistance. If I take L equal to 1 meter, length of the conductor, if I fix the length of the conductor to be 1 meter and area of cross section to be 1 meter square, then rho will be equal to R. This is how we define resistivity. No, Abdullah, it does not depend. I'll show you. I'll show you in the microscopic form that it does not depend upon length and area of cross section. Resistivity of a material can be defined as resistance of a conductor material of unit length and unit area of cross section. So resistivity is the resistance of a material of unit length and unit area of cross section is known as resistivity. So if I take L and A both equal to 1, then I will get that rho is equal to R. Resistivity will be equal to resistance. After resistivity, so if you want to see resistivity in microscopic form, say resistance is ml by A n E squared tau, right? And resistivity is like, I call this as equation number 1. Let's call this as 1. Let's call this as 2. And this as 3. So we can substitute the value of R from 3 into. If I substitute 3 into, then I will get that rho is, it's ml over A n E square tau A by L. This A will cancel this A, this L will cancel this L, and we are left with this term only. Resistivity is m by n E square tau. So you can see there is no length or area of cross section. It's absolutely independent of length and area of cross section. So resistivity is independent of length. Resistivity is independent of length and area of cross section. It does not depend upon length and area of cross section. It depends only on small n. Small n depends upon nature of material, and tau, this depends on temperature. It depends on nature of material and relaxation. Nature of material and relaxation. So these are the factors on which resistivity depends. It does not depend on length and area of cross section. It depends on nature of material and relaxation time. Now let's check its SI unit. So Fatma, what is the SI unit of resistance? This is resistivity, na? What is the SI unit of R, Fatma? Fatma, can you hear me?
Yes, sir.
What is the SI unit of resistance? Resistance.
Wait,
What?
I don't know, sir.
Resistance, ohm.
Oh, yeah.
What is the unit of area? SI unit of area, Fatma?
Meter square.
Meter square. And what about length?
Meter.
Meter. So the SI unit of resistivity is ohm meter.
Oh, meter.
Okay, note it down. We'll do one numerical on resistivity. Yes, written. Can I change this right now?
Sir, done.
Okay. Okay, let's solve some numericals also. Length of a wire is increased by 2%. Calculate percentage change in resistivity and resistance. So I take a wire of certain length area of cross section is A, the length of the wire is A. Resistivity is rho. Now I increase the length of the wire. When I increase the length, then area of cross section will decrease. When I stretch something, its area decreases. So the new length is, let's say, L prime. New area is some A prime. Mariam, what do you think? What will happen with the resistivity when I change the length? It will increase, it will decrease, or it will not change. What happened with resistivity, Mariam?
It will decrease.
It will decrease. Okay. Mariam, just read this statement, please. This statement, this one. Read this statement.
So it's
And read it loud. Mariam.
Resistivity is independent of length, area, and cross-section.
Ah.
It depends on the nature of material.
Okay, now answer this question. I'm changing the length. How will it will change the resistivity?
It will not change.
Will not change. The resistivity will remain same. Resistivity will not change. Resistivity will not change. When you change length and area of cross section, then everything can change, but not resistivity. Now, let's decide how the resistance will change. See, initially, the resistivity is rho, area is A, length is L. I can write that resistance is rho L over A. That's my first equation. This is the initial resistance, rho L by. When I change the length, I'm changing the length, so area of cross section will also change. So I can write my resistance as now rho is R prime is rho L prime over A prime. That is equation number. Abdullah, can you relate L prime and L?
Yes, sir.
How? How will you relate them?
So L prime is equal to L plus 2%.
L?
Of
Ah, yes.
2%.
L prime is L plus 2% of it, right? You are increasing length by 2%. So that's L plus 2% of it. So your L prime is L plus 2 by 100 of L. So the L prime becomes 102 L by 100. So I will get 1.02. That's equation number 3. Now I have L prime in terms of L. Now I want to convert A prime in terms of A. Now Amalia will tell this, will answer this question. Amalia, am I audible?
Yes, sir.
Yes, okay. So Amalia, if I stretch this wire, then its length will increase, its area will decrease. What about the volume of the wire? Will the volume also change?
No, sir.
Yes, Amalia, on stretching this wire, will volume also change or volume remains unchanged?
Volume will not change. Volume will not change.
Amalia speaks a bit louder.
Volume
Can't hear. Yes, volume will change or not?
it will not change.
Yes, volume will not change. Volume will not change. So I can say that initial and final volume will remain same. Initial volume will be equal to final volume. Now, Shahzada will tell me how to calculate the volume of this conductor, initial volume. Shahzada, area and length is given. What's the volume?
area and length is
Area into length. A into L is the initial volume.
Yes.
Final volume, Shahzada?
So L prime into
Very good. A prime into L prime is the final volume. Good. So now what I can do is I can substitute the volume of value of L prime from 3 to 4. Now I substitute 3 and 4. When I make this substitution, this AL is A prime into L prime, which is 1.02 L. So this L will cancel this L, and A prime is A by 1.02. It's A by 1.02. That is equation number 4. And this is something which is very obvious. If you increase length by 1.02 times, then area will decrease by 1.02 times. Okay. So you have L prime, you have A prime. Then what we can do is we have L prime, we have A prime. We can substitute these values here. Let's substitute 3 and 5 into 3 and 5 into. So when I make these substitutions, and I will get R prime is, it's rho L prime. How much is L prime, Noor?
1.02 L.
1.02 L. So instead of L prime, I'm writing 1.02 L. Ahmed, how much is A prime?
A by 102. 1.02.
This 1.02 will come to the numerator. Now I will get R prime is 1.02 square rho L by. So that's R prime. So that's equation number 5, and I take this as equation number 6. Next, what we can do is, like, we can compare 6 and 1. You can easily compare equation number 6 with equation number 1. So we can substitute 1 in 6. When I substitute 1 in 6, then I will get R prime is 1.02 square into R. So that's the relation between. And how much is 1.02 square? It should be some 1.0404. So that is the relation between the final resistance and the initial resistance. Is it clear, everyone? Fatma, Mariam?
Yes, sir.
Yes, sir.
Now I need percentage change in R. Percentage change in R. Now this is class 8 question. Huh? How to change a percentage change in any quantity? How to calculate percentage change in any quantity? Mariam? I want to get percentage change in R. How will you calculate a percentage change? No answer. Huh?
Sir, I don't remember.
Don't remember. Fatma, how to get percentage change? Abdullah, volume doesn't change. When you stretch a quantity, then its volume remains same. Shape, size, length, everything change, but not the volume. Fatma will all not on. Noor.
Don't remember, sir.
Okay. Noor, how to get the percentage change in any quantity?
So final minus initial by initial into 100.
Percentage change is change divided by initial value multiplied by 100. And how we calculate change? Change is final quantity minus initial quantity by initial quantity multiplied by 100. What is the final quantity? R prime, it's 1.0404 R minus R by R multiplied by 100. So 1.0404 R minus R is it's 0.0404 R by R multiplied by. So the percentage change that we are getting is 4.04%. So that's the rough percentage change. Oh, sorry, exact percentage change in resistance. This is how we calculate percentage change. Change in quantity divided by initial value multiplied by 100. So if you increase length by 2%, then resistance will change by 4%. There's one shortcut method also to do this thing. Like if percentage change in length is X%, if percentage change in length is X%, then percentage change in resistance is 2X%. If the percentage change in length is X%, then percentage change in resistance will be around 2X%. This is true if X is less than 5%. Means until the percentage change in length is less than 5%, this relation holds true. Like in this particular case, say length was changing by 2%. Percentage change in length is 2%. And percentage change in resistance is around 4%. It's not this shortcut method will not give you the exact result, but to an approximation, it will be correct. So Fatma, if I say that percentage change in length is 3.5%, then what will be the percentage change in resistance? Yes, Fatma. If I say that percentage change in length is 3.5%, then how much is percentage change in resistance? Fatma, I can't hear you. You can use chat room. Your mic is not there. Fatma, use this thing. I'm giving percentage change in length to be 3.5%. I'm asking about percentage change in resistance. Yes, how much is it? I'm giving length, percentage change in length is 3.5%. Don't write the entire formula. Just give me the numerical value. In length, it's 3.5%. 7%. Double of it. 7%. 7%. Remember this direct formula. If you don't have time in your exams or you are dealing with MCQs, then you can use this directly. It will save some time. Okay, just note it down. Then we'll do one more numerical on this concept. And tell me if you still have any doubt. Yes, can I change this slide?
Yes, sir.
Okay.
So this question can come for institute type or like no other as well.
If it is coming in subjective, then you have to do the complete calculation. Okay. But if it is coming in MCQ type, then you can use this shortcut. But remember, the shortcut is valid only up to when the percentage change is less than 5%. Because once the percentage change exceeds 5%, then the error increases. Error starts increasing.
So can it be 5% exact?
Yeah, then it's around 10%. Then it's 10%.
Okay.
But remember, as you keep on increasing the value of x, the error keeps on increasing. Like the exact value is 4.04%. But when you calculate with this formula, it comes out to be 4%. So you have an error of 0.04%.
Okay, so done.
Okay. The next type of questions then we can get on resistance and resistivity is this. We will give you a cylinder, like it's giving you a cylinder. The radius of the cylinder is r. The length of the cylinder is L. I need resistance, which is rho L over A. So when I write A is the area of cross section. The area of cross section of this end is pi r square. And this L is the separation between the two area of cross section. Separation between the two area of cross section is L. So resistance will be rho L over pi R square. Remember, L is always the separation between the two ends. This is straightforward. The next question is, instead of a resistor, you can have a cuboid. A cuboid of this shape. What are the number of faces in a cuboid, Shehzada? How many faces are there in a cuboid?
Just
6 faces. So I name this phase as phase 1. I'm naming this as phase 2. This is the top phase 3. This is the bottom phase 4. Then you have a front phase 5 and a back phase 6. 6 means back phase. And I'm also writing all dimensions. This is L. This is breadth, B. And this is height. Resistivity of the material is rho. Resistivity of material is rho. Calculate resistance between points. So I take first point. I need resistance between 1 and 2. I take second point. I need resistance between 3 and 4. I take third point. I need resistance between front and back phase 5 and 6. So I need resistance between these 3 points. So when I calculate resistance between 1 and 2, then while using this formula, like first part I'm solving, the rest you will solve. R is rho L by A. So the area that we will use, I have to calculate the resistance between point 1 and 2. So the area, we will use the area of this face, area of cross section of this face, and area of this face. Fatma, what is the area of this particular face? All dimensions are given. What will be the area of this face? It's like a rectangle. What would be the area of this face, Fatma?
B into H.
Yes. See, this is like a rectangle. One dimension is B, another dimension is H. So area should be B. So for R12, area that we will use is B into H. Length that I will use is the separation between the two faces. Separation between the two faces is L. So L is LA. I write this as A12. I write this as L12. So A12 is BH, L12 is L. And I substitute all these values here, then resistance will be rho L over BH. Okay, let's do second case. I need resistance between 3 and 4. So I can write R34 as rho L34 divided by A34. This is how we calculate R34. Rho into L34 by A34. Mariam, can you tell me how much is L34 for 3 and 4 phase? Mariam, how much is L34? L34, Mariam, simply means the separation between the two faces. The separation between the two faces will be L34. How much is L34? Amalia, how much is L34? The separation between the phase 3 and phase 4? Yes, Noor, you're right. Yes, Amalia.
Sir, I don't know.
See, this is phase number 3. Try this one. This is phase number 4. I need separation between these two phases. Just check this diagram and tell me what the separation between the phase 3 and phase 4. Amalia. It's easy.
H.
H is the separation. No? This is phase 3 and phase 4. The separation between them is H. So L34 is H. Next, I need A34. Mariam, try it. How much is A34? A34 means the area of this particular phase. This phase that I am using. Yes, Mariam. What would be the area of this phase?
Sir, LH.
L and see one. No. See, the one dimension is L, right? What is
Yeah.
this another dimension? This is H or this is B?
B.
This dimension is parallel to this side, right? And this side is B, so this is B. So what will be the area of this phase? 3, 4?
LB.
LB. When I substitute all values here, then I will get R 3, 4 is rho H by LB. This is R34. After R34, the third is five, 6. The front face is 5 and the back face is 6. 5, 6 face. I need resistance between phase 5 and phase 6. Okay, so Shahzada will answer this question. Shahzada,
Yes, sir.
what is the separation between 5 and 6? 5 is the front face and 6 is the back face.
So B.
B, very good. The separation between the front and the back face is this B only. So we can say that this is the expression. R 5, 6 is rho L 5, 6 by A 5, 6. L 5, 6 is B only. Now I need A 5, 6. Fatma, will you try? I need area of this particular phase, this phase. This is phase 5. And the phase opposite to this is phase 6. I need area of this phase. Sorry, Fatma, you're not audible. Can you please repeat? Fatma, your voice is cracking. I can understand. Can you write in the chat room, please? Yes, Abdullah, it will be B. Na? This is the front face and that is the back face. Separation between front and back face is B only. I need the area of this particular face. One dimension is L. Another dimension is H. So it will be AH only. Na?
So you wrote it as H. It should be B.
Yes, sorry. It should be. One is L, another is H. So when I substitute these values here, R5, 6 becomes its rho, it's B over LH. This is the second type of questions that one can get on resistance. These two type of questions are given in NCERT. One, where the percentage change in length is given and is supposed to calculate percentage change in resistivity. The second is this question, where a shape will be given. Most probably the shape would be a cylinder or a cuboid, and you're supposed to calculate the resistance between the faces. Yes, can I change the slide?
Yes, sir. Said I. Sir, till what time will teach?
Maybe around 12:15, 12:15. Sorry, according to you, it's 9:30, 10.
Okay, sir.
Okay, can I change the slide now?
Yes, sir.
Okay, after these terms, resistance and resistivity, the next is conductance. Conductance is the inverse of resistance. One by R. That's the inverse of resistance is known as conductance. Is a SI unit is ohm inverse. Ohm inverse. It's 1 by rho SI unit is ohm. Then after conductance, we have conductivity. Conductivity is the inverse of resistivity. It's inverse of resistivity. We represent it by sigma, and this is 1 by rho. So its SI unit is ohm inverse meter inverse. After conductivity, next we have current density. These are few definitions that we may use. Current density is current per unit area. Like if I give you a conductor, the area of cross section of the conductor is A. The current flowing through it is I. So the current density, we represent it by J, and its current per unit area. Its current per unit area, J is I by. Its SI unit is it's ampere per meter square. That's the SI unit, ampere per meter square of current density. And remember, current density is a vector. Its direction is same as that of current. Is same as that of current. The direction of current and current density is same. There's one more important relation which is known as microscopic form of Ohm's law. Microscopic form of Ohm's law. And that expression is this: J is equal to sigma E, where J is current density, sigma is conductivity, E is electric field. Note it down. Written. Can I change the slide? These are some basic definitions that one should remember. Yes, Fatma. See, the next definition is mobility. Mobility is basically its ratio of drift velocity and electric field. It's drift velocity per unit electric field. Drift velocity per unit electric field is mobility. So we represent mobility as mu, and this is the ratio of drift velocity and electric field. This is mobility. The SI unit of mobility is, the unit of drift velocity is meter per second. Unit of electric field is volt per meter. So this is meter square per volt per second. That's mobility. Meter square per volt per second is mobility. It's mu. Mu. This is known as mu. These all are one marker questions. You don't get much numericals on this topic. These are, you should remember these definitions, these basic definitions. Any doubts in these definitions? Conductance, conductivity, current density, or mobility. Any doubts in these definitions?
No, sir.
After these definitions, the next is the temperature dependence. Like how resistance varies with temperature. That's the last topic, theoretical topic in current electricity. That's temperature dependence of resistance as well as resistivity. Like how resistance or resistivity vary with temperature. Temperature dependence of resistance and resistivity. So how temperature varies with resistance and resistivity. See, for the difference between resistance and resistivity is only length and area of cross section. For the time being, the temperature range that are involved, like if I draw resistance, R is rho L by A. Sorry, no. This is the formula of resistance, ml by A N E squared. And this is for resistivity, m by N E squared. So for the temperature range involved, there is not any significant change in length and area of cross section. So for the temperature range involved, there is no significant change in length and area of cross section on changing temperature. So resistance and resistivity will have same variation. Resistance, both resistance as well as resistivity will have exactly same variations. So we'll see this variation. So the variation in resistance or variation in resistivity is same for the temperature range involved. First, do it for conductance. Rho is m by n E squared tau. So if I increase temperature, then mass will not change, like this electronic mass, which is independent of temperature. Electronic charge will not change, but on increasing temperature, the relaxation time will decrease. On increasing temperature, there's no significant change in number density. Number density is almost constant. Although there is increment in some number of electrons, but in conductors already you have millions of electrons, so the change will not be significant. So if tau decreases, then R will increase, or R or rho will increase. I'm repeating again. If I increase temperature, then mass will not change, N will not change, charge will not change, but relaxation time will decrease and its denominator. So if it decreases, then rho will increase. So on increasing temperature, resistivity increases. So in conductors, on increasing temperature, rho and R both have same variation, increases. So if I plot graph, this is the shape of the graph. This is temperature in Kelvin. And this is resistivity or resistance. So this is the variation. This is how resistivity increases with temperature. This temperature is 273 Kelvin. So you can see up to 273 Kelvin, this variation is non-linear. This is a bit curved. Then after 273 Kelvin means 0 degrees Celsius, this relation will be linear, straight line. So you should remember this result. It's an important one marker question. Like up to 0 degrees Celsius, variation is non-linear. Non-linear. Beyond 0 degrees Celsius, it's linear. After 0 degrees Celsius, the relation is bit linear. It's a linear relation between. You can take resistivity or resistance, will get the same graph. After conductors, we have alloy. What are alloy, Shahzada? What are alloy?
It's a mixture of two or more.
Mixture of two or more metals, right? So alloy is a type of conductor. Metals are conductive. So alloys is also a conductor. So the difference between variation of conductor and alloy is, in alloy also resistance or resistivity increase with increasing temperature, but the variation is small. In alloy, resistance and resistivity increase with increase in temperature, but variation is very small. So if I draw this graph for alloy, the slope is very small. Like variation, there is variation, but that variation is very small. This is for alloy, resistance and resistivity. After alloy, we have insulators or semiconductors. We have insulator and semiconductor. So this is resistivity. The expression of resistivity is m by n e square tau. When I increase temperature, see, this will not change. This will not change, but relaxation time will decrease. Due to decrease in relaxation time, resistivity should increase. The next effect is on number density. When I increase temperature of an insulator or semiconductor, then number density will also increase. Some bonds will break, new free electrons will generate, due to which, see, this n is in denominator. If this n is increasing, then rho should decrease. So you can see one effect is trying to increase resistivity. Another effect is trying to decrease the resistivity. So the overall effect will depend upon the stronger one. Here, this is the stronger effect. This is stronger. So on increasing temperature, resistance and resistivity decreases. So if I plot the graph, this is temperature in Kelvin. This is resistance or resistivity. This will be the graph. If you increase temperature, then resistance will decrease of insulator and semiconductor. There are few more important graphs, like instead of resistance, if I ask you to plot resistivity, this could be a 1-marker question. Resistance and resistivity, if I ask you to plot conductivity. Conductivity is inverse of resistivity. So if resistivity is increasing, then conductivity Sorry, it got disconnected. Have you noted those terms?
Yes, sir.
Everyone?
Not all.
Not all. Okay, I'm not writing it again. I'm just sharing a PDF. Okay. You want to write everything again.
Okay, sir.
So within an hour, I will ask Nishkash to share a PDF having all these terms. Okay. So that was about temperature. The important thing is if you take a conductor and if you increase temperature, then resistance will increase. If you take an alloy, then also on increasing the temperature, resistance will increase. But if you take semiconductor or insulator, then if you increase temperature, then resistance will decrease. This is the important thing. The rest I will share in a PDF if you can't write. If you have not noted. Just note this thing. That's important. This you should remember. For conductor, on increasing temperature, resistance increases. An alloy, on increasing temperature, resistance decreases. And same for insulator. Just tell me once you have written.
Sir, done.
The next is after this thing. Okay. Now we know qualitatively how resistance varies with temperature, like on increasing temperature, how resistance varies. Next is one more variation is for superconductor. Superconductors are very interesting materials. Like at some temperature, the resistance of superconductors becomes zero. Resistance vanish completely. They are superconductors. So if I plot a graph temperature in Kelvin and resistance, resistivity. Then this is the graph of superconductor. If you keep on decreasing the temperature, the resistance keep on decreasing. At some temperature, the resistance becomes zero. This temperature is known as critical temperature. Critical temperature. We use superconductors in bullet trains. We use superconductors in MRI tests like MRI. We use superconductors. So superconductors are those materials which have exactly zero resistance at some temperature, which is known as critical temperature. Slow it down.
Sir, done.
Okay, all these discussions were qualitative. All these discussions are qualitative. We have some mathematical relations also to get the value of resistance at different temperatures. Yes, Noor, at absolute zero, resistance of every pure material is zero. But it's not possible to attain absolute zero. Even in lab, you can't attain exactly 0 Kelvin temperature. The minimum temperature that people have attained is this, not absolute zero. So for superconductors, the temperature is not 0 Kelvin. At some non-zero Kelvin, like around 250 Kelvin, 230 Kelvin, 200 Kelvin, you can get zero resistance. Variation of resistance with temperature. Variation of resistance with temperature. So let's say you have some, some resistance R naught at temperature T naught. R naught is resistance at some reference temperature T naught. And that reference temperature is usually 0 degrees Celsius or room temperature. So this is a temperature at which you know your value of resistance, that is R. You're supposed to calculate resistance at some temperature T. Where T is greater than T. I will use a constant alpha, and alpha is known as temperature coefficient of resistance, and that's it. So at temperature T, the resistance can be written as it's R naught, 1 plus alpha, it's T minus T. This is the resistance at temperature T, which is R naught, 1 plus alpha, T minus T naught. This is temperature coefficient of resistance. Its SI unit is Kelvin inverse. For different material, this alpha will have different value. But basically, the value of alpha will depend on material. So using this simple relation, you can calculate resistance at different temperatures. But you should know the resistance at reference temperature T naught. Then you can get resistance at any temperature. Just note it down. Yes, noted.
Yes, sir.
Okay, so I'll stop here. Tomorrow I need a class. So tomorrow I will finish this thing and we'll start Kirchhoff law. Can we have class in the morning tomorrow, or you have school?
No, sir, no school tomorrow.
No school tomorrow. So let's have a class the same time, like 8 to 9:30.
Okay, sir.
Morning, Abdullah. Evening I have other lectures. So tomorrow I will finish this thing and we'll try to finish Kirchhoff law also. So by Monday, we'll finish the chapter.
Okay, sir.
But please revise, like you don't remember, most of you don't remember anything from the past chapters. Please start revising your chapter number 1 and chapter number 2. Okay, so let's stop here. We'll start this tomorrow at the same time.
Thank you, sir.
Thank you, sir.
Okay, thank you.